Hello everybody, this is the video for section 9.5, which is on sequences. This is going to form a big basis of what we're going to be looking at for the rest of this chapter, or the rest of chapter 9. So we're going to be introducing this idea of sequences. So we should define what a sequence is. A sequence is, or this is right here, a listing of objects occurring in some specific order. So the order is going to be really important. If we reorder the objects, then we would get a different sequence. So the order is going to be really, really important. The book lists through 5 different possibilities of a sequence, and so I wanted to give examples of what those were so you could see the different ways that sequences could appear. So probably the most basic one would be this number sequence. So 1, 2, 1, 2, 1, 2. And we see these 3 dots here, which means the sequence is going to continue. And hopefully you'd be able to see that the next term in the sequence would be a 1, and then another 2, and then a 1, and then a 2. We have enough things listed, we have enough elements listed in the sequence that we can predict what's going to happen from there on out. We'll come back to that at the end of this video, though. We've got, for letters, ABB, 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 and again, you should be able to tell what's going to follow next in that sequence. That it would be another ABB, then another ABB, and so on, so on, so on. We've got figures, so we've got the 1 asterisk, the 2 asterisks, the 3 asterisks, the 4 asterisks, the 5 asterisks. It's kind of hard to give a lot of examples of this because a lot of these are things that would kind of need to be drawn or shown. The book shows some examples of this where you've got dots that are sort of expanding out, a purple dot with some orange dots kind of radiating out from it. So there's some examples in the book that show figures, but this gives you the basic idea of what's happening in those figures. So again, you could figure out what the next element in that sequence would be. There would be 6 dots and then 7 dots and then so on, so on. Objects and figures, there's a lot of overlap between here, but the way I sort of understood it was to be that a figure was something that was a physical object that was going to change, whereas objects would be just like one sort of static object. So for objects, we have exclamation point, @sign, pound sign, exclamation, @sign, pound sign. So again, we see the pattern that's emerging from that sequence. And then lastly is movements, and I'm glad this book mentions this because this idea of doing things with movements. So like your right foot forward, right foot back, left foot forward, left foot back, and you could repeat that left forward, right back, left forward, left back, right forward, right back, left forward, left back, and keep doing that. This kinesthetic idea hits that multiple intelligence aspect for a lot of students that maybe they don't get to do in math class a lot, that kinesthetic sense. There's a great book, and there's a picture of it there, called Math on the Move, where if you are interested in math education and interested in incorporating more kinesthetics into your math teaching, it's aimed at elementary school teachers. I mean, you can kind of tell by the size of the shoes on the cover there. So if you're thinking a little bit more about upper grades or even middle school, it may not be as appropriate, but I still think it's a fantastic book. So if you're interested in this idea, it's definitely worth checking out. There's a system that we can use to classify patterns. And so if we look at this pattern here, this is 1, 2, 3, 5, 6, 7, 8, 9, 10. So one of the things that you might notice is that we don't have a 4, we don't have an 8, and we're probably not going to have a 12. And so these are occurring in little blocks of 3. So this 1, and then add 1, add 1. And then skip a number, add 1, add 1. Skip a number, add 1, add 1. And so we can classify this as being sort of A, B, C, A, B, C, A, B, C. We see these things sort of occurring in these 3 number blocks. Now, we don't want to use A, B, 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 C, 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 because depending on how long we have to write this thing out, we might run out of letters. So we use the ABC to show this is a block, and then ABC to show the next block, and ABC to show the next block. If you look at the examples on the previous page, you can try to figure out what those might look like. funny enough, the pattern, the letter pattern was ABB, 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 which we would show by just being ABB, ABB, ABB. And we could use the B's consecutively because it's the same letter consecutively. So we could use that. If you've done any sort of like poetry analysis, then you've seen this sort of idea before, that you know, like an ABAB rhyme scheme or an AABBA in the case of a limerick rhyme scheme. In this same sort of idea. So there's an interdisciplinary connection there between looking at patterns and looking at poetry. So it isn't a huge thing, but it does give us a way to sort of classify these patterns. How much you want to use this with your class is going to be dependent on the maturity and the sophistication of the class. This might be something that you use just for yourself to make sure that you're not always using AB patterns, that you're incorporating things that are a little bit more complex, that you're not doing the same thing. So you may use this with students, you may not use this with students. I mean, it's entirely up to you. So let's look at the first of two different types of sequences we're going to need to define in this section. The first one being the arithmetic sequence. An arithmetic sequence is characterized by adding or subtracting the same amount each time. So I've got three examples here. We can see 1 to 3, I'm going to add 2. From 3 to 5, I'm going to add 2. From 5 to 7, I'm going to add 2. Add 2, add 2, add 2. So we can see what the rule is here, that we're adding 2 each time. And we could use that rule to generate the next terms in the sequence. We know this would continue 17, 19, 21, so on, so on, so on. So again, we're adding or subtracting the same amount each time, and that's what makes this an arithmetic sequence. Here we can see that we're adding 5 each time. And we've started at 5. We're not always going to start at 1. So make sure that when you're doing these in class, you don't always start at 1 or start at 0. We want to change our starting value. And then here, we're not adding, because we can see the sequence is decreasing, we're actually subtracting 3. So minus 3, and so on and so on. So adding or subtracting. Now this is a counterexample. This doesn't work. So why doesn't this work? Well, if we look at this, and I'll do this in a different color, so we can see that it doesn't work. I'll do it in blue. So here we've got plus 1, and then here I've got plus 2. Plus 1, plus 2. Now, this is a pattern, and this is a sequence, and I can tell what's going to happen each time. Add 1, add 2, add 1, add 2. But it has to be the same amount. So because the amount that I'm adding is changing, this is not an arithmetic sequence. This is a sequence. So it is a sequence, and it is a pattern, but it's just not an arithmetic sequence. Right? So it is a sequence, it is a pattern, it's just not an arithmetic sequence. We can use the sequence from the previous page to illustrate a really important point about sequences, and it's a really important point that we're going to need for the rest of the chapter. We're going to take these terms and we're going to put them on some axes. And by axes, this means we've got two lines here. We have our x-axis and our y-axis. And we're going to label the x 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And so the term number 1, 2, 3, 4, 5, 6, 7, 8. So these are my x values up here. And this is the order in which it appears in the sequence. Now, you could start counting at 0, you could start counting at 1, you could start counting at 5 if you're so compelled, but we're typically going to start at 1, although you may see in other books and in other resources starting counting at 0, and that's fine, but we're just not going to do that here. Now the value of the sequence, the actual sequence, is going to be our y value. And so if I look at this first term in the sequence, it's the first term, so it's a 1, and the value of the term is a 1. So we're going to put a little dot there to show that term number 1 has a value of 1. And now if I go to the second term of the sequence, that's going to be at 2, and it has a value of 3. And then term number 3 has a value of 5. Term number 4 has a value of 7. Term number 5 has a value of 9, and so on and so on. Now, what we should notice here is that this forms, that didn't work out so well. This forms a straight line. Let me erase this because that straight line is terrible looking. So this forms a straight line, which is a little bit hard to do on this tablet, but let's see if I can, oh, that's not bad. Okay. So we can connect these together and we see that these form a straight line. Now, how much this changes from term to term, this is going up by 2 each time. I'll switch back to red. So this is going up by 2 every time our term increases by 1. Now, some of you probably know where this is going, and we're going to get there soon enough. So we're headed toward an idea here that we'll get to in the next couple sections. But for right now, I want you to really think about this as a rate of change. It's how much the sequence is changing as we move from term to term, from consecutive term to consecutive term. We'll look at larger rates of change later on, but for right now, I just want you to appreciate that as we move from one term to another term, that we have this change. And that this forms what we call a linear relationship. If you ever get confused about linear relationship, just look at the first 4 letters of linear. I mean, it's line. And it tells you what it is right there. So a linear relationship is something that's going to form a straight line. Not a curvy line, but a straight line. And so we can see that this is a linear relationship. If you wanted to go back to the previous last example where we did plus 1 plus 2 plus 1 plus 2, if you want to take the time to graph that, you'll see that it doesn't form a straight line. It forms almost like a zigzag, like a jagged sort of pattern. So it's not a straight line. It forms that jaggedness, and so that means that shows a representation that it's not a linear relationship. The other type of sequence that we need to look at is called a geometric sequence. So a geometric sequence is a lot like an arithmetic sequence, but instead of adding or subtracting the same amount each time, we are multiplying or dividing the same amount each time. So if you look back at that last example that we did in arithmetic sequences, it's not arithmetic because we're not adding the same amount or subtracting the same amount each time, but it's also not geometric because we're not multiplying or dividing the same amount each time. So don't fall into the trap of thinking that every sequence has to be arithmetic or geometric. A lot of the sequences you're going to see are going to be neither, and that's okay. A sequence can just be a sequence that's not arithmetic or geometric. So here we can see we're multiplying by 3, we're multiplying by 3, we're multiplying by 3. Now, if I tried to check and see if this was arithmetic, you could see we have plus 2 and then plus 6. So we're already done. We can tell straight away this is not arithmetic because we're not adding the same amount each time. As it turns out, it is geometric. Same thing down here for the second one. We could see what we are, let me erase this because we don't really need it now. So 1/4 to 1/2. It's a little bit tougher because we got some fractions to deal with, but we're multiplying by 2, we're multiplying by 2 times 2 times 2, and so on. And so this is geometric because we're multiplying by 2 each time. This is a little bit more difficult. Here we're dividing by 5 each time. So 1250 divided by 5 is 250, divided by 5 makes 50, divided by 5 makes 10, divided by 5 makes 2. The next term in the sequence would be 2/5, 2/25, and so on and so on. Now, you could think of this as also we're multiplying by 1/5, which does the same thing as dividing by 5. So either one of those would work, and they both allow it to be a geometric sequence. This pattern at the bottom, again, is a counterexample. It shows a definite pattern, and we see what this pattern is. We've got 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1. And so we've got some ones with an increasing number of zeros on the inside. So I could tell that the next one's going to be 4 zeros, 1, 2, 3, 4, 5 zeros, so on, so on, so on. This is not arithmetic. I'm not adding the same amount each time. And it's not geometric. I'm not multiplying by the same amount each time. So this is not geometric. It's not arithmetic. It's just a sequence. It's just a pattern. So I just want to show a counterexample so you can see what something looks like that's not a geometric sequence. We could do the same thing graphically here that we did for the previous example. So we've got our X, we've got our Y. We'll make a little table here. We've got 1, 2, 3, 4, 5, 6. And so we'll graph this. So 1 goes to 1. And then 2 goes to 3. So my second term is a 3. My third term is a 4, 5, 6, 7, 8, 9. Now, you hopefully should be able to tell this is not linear, because from 1 to 2, my rate of change was 2. So we'll put this arrow back in. So here I've increased by 2, but here I have increased by 6. So I can tell this is not linear. My rate of change is changing. So that's what makes this not linear. We'll talk a lot more about this changing rate of change in the next couple of sections. We're not going to do an awful lot with graphing this type of thing, especially because now the next number is 27. So this graph starts to get pretty huge. But this is the larger point I wanted to make, that we can see if we graph this much of the function out that it's not linear. The book mentions this, and this is a really good point, that we want to be careful about ambiguous sequences. So if we look at this sequence, and we want to know what the next term is, there's a couple of different answers. And what makes this ambiguous is that there's not a lot of terms given at the beginning. The fewer terms that you give in a sequence, the harder it's going to be to really uniquely determine what the sequence is doing. So one way we could think about this sequence is that we are adding one more each time, that the rate of change is increasing. So this is +1, this is +2. So the next one, this is +1, this is +2. So the next one would be +3, makes 8. The next one would be +4, makes 12. Next one would be +5, makes 17. And that totally works. And that would absolutely work. We're going to see later on, this is going to be an example of a quadratic sequence. But this absolutely works. So this is a form of a sequence. This could also be 2, 3, 5, 7, 11, 13. So this could be the sequence of prime numbers. And that works as well. That's also a defined sequence. So we want to be really careful when we give a sequence, that we give as many terms as we can, so that we can really see what's going on in the sequence and it's not ambiguous or vague for our students or for ourselves. So for your checkpoint, I want you to think about an example of an arithmetic sequence. I want you to think about an example of a geometric sequence, obviously other than what I've given in the video and what's given in the book. So try to come up with your own. And then try to come up with a sequence that's neither arithmetic or geometric, and be able to explain why it either is arithmetic, why it is geometric, or why it is neither. So I just want you to come up with examples for your checkpoint problem. If you have any questions about this, by all means, please bring them to class and we'll answer them. All right, thanks.